When you look at a professional camera or a high-end microscope, you see a sleek cylinder of metal and glass. From the outside, it looks like one solid, unified tool. But if you peel back that casing, you won't find a single thick piece of glass doing all the work. You'll find 5, 6, or even more distinct curved lenses, precisely aligned in a row along a single axis. This setup introduces a specific engineering challenge. We know how a single lens bends light, but we need a way to track a beam as it passes through a gauntlet of multiple curved surfaces, one immediately after the other. The goal is to make these individual components work together as if they were one single lens with an exact effective focal length. Focal length is the distance from the center of a lens to the point where parallel light rays converge. Instead of relying on impractically thick and heavy blocks of glass, optical engineers use the principles of thin lens combinations. By understanding exactly how light passes from one lens to the next, they can stack simple elements to build highly precise instruments. This schematic shows a simplified version of that stacking technique. We have an object, marked O, sitting on a central axis, facing two thin convex lenses, lens A and lens B, placed in direct contact. Let's track the light as it leaves the object. To understand the physics, we first look at lens A in isolation. Rays travel outward from the object, hit the first lens, and bend inward toward a convergence point. We can call this convergence point the ghost image. It is exactly where lens A would have focused the light if it were floating alone in space. We'll label this theoretical point I1. In a multi-lens system, the image formed by the first lens serves as the object for the second lens. Here, the convergence point I1 functions as a virtual object. A virtual object is a point that light rays are converging toward, but are intercepted by another optical element before they actually reach it. We call it virtual because the physical light never reaches that distant spot. Lens B sits directly in the path, intercepting those converging rays while they are still in transit. Lens B takes those incoming rays and bends them a second time. This final bend forces the light to converge at a new point on our axis. This is our true final image, labeled I. A multi-lens system operates like an optical relay race. The first lens shapes the light and hands that theoretical ghost image off to the next lens in line, which bends it further until it reaches the final focus. This diagram shows the math behind the relay pass, starting with lens A. We use the standard thin lens formula. 1 over V1 minus 1 over U equals 1 over F1. Here, U is the distance from the lens to our original object, and V1 is the distance to the theoretical ghost image. Now we apply the formula to lens B. Because the second lens treats the ghost image as its starting point, we plug V1 into the object position. That gives us 1 over V minus 1 over V1 equals 1 over F2. Notice the V1 term sitting in both equations. That is the shared link, the mathematical representation of the handoff between the two lenses. To find the net effect of the entire system, we add the two equations together algebraically. When we do, the positive 1 over V1 and the negative 1 over V1 cancel each other out. The remaining variables drop down, giving us a unified equation. 1 over V minus 1 over U equals 1 over F1 plus 1 over F2. The math perfectly reflects the physical world. Stacking two thin lenses creates a system that acts exactly like a single equivalent lens, where the total focal length is the sum of the individual inverses. While these equations work, calculating the inverse of multiple fractions is a slow process for engineers. To streamline these calculations, they convert focal lengths into a metric called optical power. Optical power is defined as the reciprocal of the focal length, measured in diopters. A diopter is a unit where 1 diopter equals a focal length of 1 meter. This provides an efficient method for calculating lens combinations. The net power of the entire system is simply the algebraic sum of the individual lens powers. The algebraic nature of this sum is critical. Convex lenses converge light and have a positive power, while concave lenses diverge light and have a negative power. By combining a +5 diopter convex lens with a -2 diopter concave lens, engineers reach a net system power of +3 diopters. Although optical powers add together to find the system's strength, the magnification of the resulting image follows a different rule. When thin lenses are combined, the total magnification is the product of their individual magnifications. This multiplication is the mechanism that powers compound microscopes. The first lens magnifies the object, and the second lens multiplies that already enlarged image, allowing for massive amplification without the distortion caused by a single excessively thick lens. In optical physics, the whole is the sum and the product of its parts. By stacking simple positive and negative elements, engineers combine their powers and multiply their magnifications to bring the invisible world into clear focus.